Dear students, so in this class now let us discuss about Riemann's method. Riemann's method involving Riemann's function. So for Riemann's method, so let us first consider the canonical form of linear second order hyperbolic equation. That's of the form, canonical form of linear second order hyperbolic equation of the form L of u equals uxy suffix uxy plus a ux. Ux means d by dx of del by del x of u. So aux plus buy aux plus buy plus cu equals f of xy. L of u equals u of xy plus aux plus buy plus cu equals f of xy, where a, b, c and f are the functions of x and y. Also they are the differentiable functions of x and y. Okay. Now consider v of x be another function. That v of x is another function. So v of x be a function having continuous second order partial derivatives and which is defined as m of v. M of v equals vxy. M of v equals vxy minus av of x. Av of x, that is av of x means it is axb plus avx minus bvy. bv of y means it is by v plus bvy plus cv. So listen, here first we consider the canonical form of a linear second order hyperbolic equation, which is L of u equals uxy plus aux plus buy plus u equals f of xy, where a, b, c and f of xy are continuously differentiable function for x and y. A of xy, b of xy, c of xy and f of xy are continuously differentiable functions for x and y. Now we define another function v of x in this way, having second order partial derivatives. M of v equals vxy minus av of x minus bv of y plus c. Then what is vuxy? vuxy, consider vuxy minus uvyx. uvyx. What do you get? vuxy minus uvyx is nothing but it is vyux plus vuxy minus uxvy minus uvxy. So this is nothing but that equals it is vuxy minus uvyx equals vyux plus vuxy minus uxvy minus uvxy. So plus uxvy and minus uxvy are cancelling each other. What means it is vuxy minus uvxy. Okay. So vuxy minus uvxy is nothing but vuxy minus uvy of x. Agree? So then what is vaux? vaux. So here vaux, or we consider this avux. avux. It is avux minus uavx. uavx. What is it? This is nothing but it is by the difference product rule. It is ax vu plus a vxu plus avux. Okay. Minus again uaxv or as axuv minus auvx. So plus minus auvx and plus AU Vx are cancelling each other. Okay, again plus AX VU minus AX VU are cancelling each other. What remains there? AB UX. So this is nothing but AB UX. So we have AB UX is nothing but ABU X minus U into AVX. Similarly, BBUY. Similarly, BBUY equals, it is BBUY minus U into, yes, minus U AVY. Okay. So consider these terms. Now, consider an adjoint operator. Here M is nothing but, now we define this M is nothing but an adjoint operator of U. Sorry, L. M is nothing but an adjoint operator of L. Why? Because consider V of LU, V into LU minus U into MV. VLU minus V of V into LU minus U into MV. What is V into LU? It is VUXY. V into UXY. Then plus AVUX plus BVUY plus CUV, then plus CUV, then minus U into MV. What is U into MV? U into MV means UVXY, then minus of minus plus. So it is U into AVX plus U into BBY plus CUV. Sorry, minus CUV. Okay. So minus CUV and plus CUV are cancelling each other. And what remains here? So it remains as, it is nothing but, it is treated as some UX plus VY. V into LU minus U into MV equals UX plus VY. After rearranging this one, you have this UX equals, what is UX? You have UX plus VY where U equals, what is U? U equals AVU. U equals A into VU minus UVY. Listen, it is nothing but a UX plus VY where UX equals, or VU equals AVU minus UVY, and V, what is V? V equals BVU. BVU minus VUX. VUX. Agree? So consider these two equations. You can rearrange this one, or you can, yes, U equals this one. So what is UX? AXVU plus AVXU plus AVUX, yes, minus UX VY minus UVXY. Agree? From here. Similarly, VY. Enough. So finally, L of V into L of U minus U into M of V, where L of U be the canonical form of hyperbolic equation, and V of x be a continuous function having second order partial derivative. It is defined as in this way. Then V into L of U minus U into L of M of V is nothing but UX plus VY, where U equals, this is an important term, where U equals AVU minus UVY, and V equals BVU minus VUX. So this is capital U and capital V. Okay. Here M is said to be the adjoint operator of L. If M equals L, then M is said to be a self-adjoint operator. Okay. So this is the introductory part of this Riemann's theorem. Now, in this Riemann's method, first we consider the Green's function. What is a Green's theorem? Consider Green's theorem. So Green's theorem states that, this is an important theorem, Green's theorem. The theorem states that let C be a closed curve that bounded the region of integration D. U and V are differentiable functions in D. So consider let C be a closed curve. C be a closed curve bounding the region of integration D. U and V are the differentiable functions in D and continues on this C. Then Green's function states that Green's theorem states that double integral over this D of ux plus vy dx dy equals surface integral over C u dy minus v dx. So this is the statement of Green's theorem. Let us C be a closed curve bounding the region of integration D. U and V are the differentiable functions in D and continues on C. Then Green's theorem states that double integral over D ux plus vy dx dy is nothing but integral over C u dy minus v dx. So this is the Green's theorem. This is an important argument. Agree. So far, consider the Cauchy problem. Consider the Cauchy problem for second order linear hyperbolic equation. The second order linear hyperbolic equation means it is L of u. We know that the second order linear hyperbolic equation is, we know that it is L of u equals uxy minus aux plus bvy, uxy plus aux plus bvy plus cu. That is nothing but a function where a, b, c are the differentiable functions of x and y. So this is the second order linear hyperbolic equation. L of u is uxy plus aux plus bvy plus cu equals f of xy. A, b, c are not constant. They are nothing but the differentiable functions of x and y. Okay. Now consider a smooth curve. Let gamma be a smooth curve. This is gamma. Gamma be the smooth curve. Then, so the curve is continuous. Gamma be a smooth curve which is continuous. Now assume the tangents. The tangents to this curve gamma, which is nowhere parallel to x and y axis. The tangent to this gamma, to this continuous smooth curve, which is nowhere parallel to both x and y axis. Because tangent, which is nowhere parallel to, no, it is not parallel to x and y axis. Okay. Now consider this one. Let Q and R are any two points at the end points of this curve. Then consider this point P. So P alpha beta. So P of alpha beta be the point at which the solution of the Cauchy problem is sought. Why? Because consider this Cauchy second order linear Cauchy problem. That is L of u equals uxy plus aux plus bvy plus cu equals f of xy. X equals c1 and y equals c2 are the characteristic of this equation. That's an important point. X equals c1, where c1 and c2 are constants. X equals c1 and y equals c2 are the characteristic of this equation. So here alpha and beta are any two constants. Then P alpha beta be the solution of this hyperbolic equation at which the point P, the solution be sought at the point P alpha beta, because x equals alpha and y equals P alpha beta means the coordinates are x equals alpha and y equals beta, means x equals c1 and y equals c1 be the characteristic of this hyperbolic equation. So we have x equals alpha and y equals beta are the characteristic of the curve. Agree. So means the tangents to this curve, this smooth continuous curve QR or gamma, which is nowhere parallel to x-axis, and let P alpha beta be the point at which the solution of the hyperbolic equation holds. Agree. Now let the characterization of P or the characterization of P that intersects the initial curve at 2 points Q and R. Then consider this PQRP. That's a closed curve. PQRP be a closed curve that is bounding the integration D or bounding the region of integration D itself. PQRP be the closed curve that is the region of bounding the region of integration D. Then by Green's theorem states that double integral over ux plus vy dx dy is nothing but integral over c u dy minus v dx. Now come to that curve. Here double integral over d. Now consider double integral over d. It is ux plus vy dx dy is nothing but what is ux? We know that u equals avu minus uvy and v equals bvu minus vux. So, but we know that ux plus vy is nothing but yes, it is v into L of u minus u into m of v. In previous argument, we know that ux plus vy equals v L of u minus u m of v, where u is avu minus uvy and v is bvu minus vux. Also we prove that v L of u minus u m of v is nothing but ux plus vy. So you can replace that value here. So this is nothing but double integral over d. It is v L of u, v into L of u minus u into m of v is dx dy. Okay. So which is nothing but that equals, then come to the curve, which equals integral, that is, then this is the left side, integral over ux, double integral over ux plus vy dx dy is nothing but this one, that equals integral over c u dy minus v dx. What is u? C be a closed curve, C be a closed curve that is bounding the region of integration d. Instead of c, here the closed curve is PQRP. Instead of C, here the closed curve PQ, yes, it is PQRP with the closed curve. So integral over C u dy minus v dx is nothing but it is integral from where to where? Integral from P to Q. So integral P to Q, it is u dy minus v dx plus integral Q to R u dy minus v dx plus integral R to P u dy minus v dx. Okay, but listen, along RP here x is constant. So along RP, what is dx? Dx equals 0, and along PQ y is constant, so dy equals 0. Okay, therefore this is nothing but integral over P to Q along PQ dy equals 0. So it is minus integral v dx plus along QR, there is no change, so it is along QR integral u dy minus v dx plus along RP dx equals 0, so it is along RP, it is u dy. Okay, so finally means we have double integral over d v L of u minus u m of v dx and dy is nothing but minus integral P to Q v dx plus integral along Q to R u dy minus v dx plus integral along R to P RP u dy. Clear? Okay. Now we consider, mark it as 1. Now we consider integral along P to Q, integral along PQ, integral along PQ v dx. What is integral along PQ v dx? Equals integral along PQ. What is v? V is there. It is v vu minus v ux dx. So it is along v vu dx minus integral p to q v ux dx. Okay, that is p dx. Then plus introducing a term here, integral pq. It is u vx. U vx dx minus integral pq u vx dx. Introducing u vx dx and minus u vx dx simultaneously there. So what I get? That equals integral along pq. That means integral along pq. Yes, it is that is integral along pq. V as u vx plus v ux dx this can be rearranged as equals integral along PQ. It is yes, u vx plus v ux. V is nothing but there is a plus, not negative sign. These are plus. So it is integral u vx plus v ux dx from these two terms. Okay. Yes, plus integral along PQ. It is v vy dx minus u vx dx. So it is u into vv minus u dx. Okay. So what is this one? This is nothing but the derivative of uv. uvx plus uvx plus vux is derivative of uv. So integral of derivative of uv, that is uv itself. Okay, this is uvx plus vux. What is uvx plus vux? Derivative of uv. So it is integral of derivative of uv with respect to x, the function itself. So it is uv from where to where? Along PQ. uv along PQ plus what remains? Integral along PQ u into bv minus u dx. So integral along PQ v dx is nothing but uv along PQ plus integral along PQ u bv minus u dx. Agreed. So what is uv along PQ? uv along PQ means it is uv along q minus uv along p plus integral along PQ u bv minus u dx. Okay. Therefore, double integral we start from here. Therefore, double integral over d. Yes. That means double integral over d v L of u minus v into L of u, v L of u minus u m of v dx dy equals u uv along q minus uv over b, okay, plus integral from p to q or integral along p to q u into bv minus u dx. Clear? Then rearrange that one. That is from here, what is UVP? UV along P. UV on P equals double integral, bring that one to here. So it is